This video will be on section 11.1, exponential functions. And what we'll do is we'll define what an exponential function is and then the number e. Just go ahead and point out now the reason why it's going to be called the number e is because it's really the exponential number. That's what e stands for, exponential. Then we'll look at the basic properties of exponential graphs, actually dealing with graphing a couple, and then word problems involving exponential functions. Now, this will really lead into the last section of the class. The last section of the class is word problems involving exponential functions as well, but there will be more stuff once we get there, and this will just be a little preview. All right, so what is an exponential function? The formal definition, let a, b, and k be any real numbers with the condition that b is greater than 0 and b is not equal to 1. Now, I'll explain this in a second, but for now, b must be positive and it cannot be 1. Then an exponential function f is written as f of x equals a times b to the x plus k. So what's very important here, why is this an exponential function? It's called that because x is in the exponent. So if x is in the exponent, it is called an exponential function. It's very different than having like an x squared where x is not in the exponent. X would be what we call the base there. All right. So that's what an exponent, this is really the defining characteristic of an exponential function. So b is called the base. The reason it has to obey the rules above is to make sure that so it has domain of minus infinity to infinity, and the reason it can't be 1, normally it could be 1 and that's fine. The negative numbers are what's bad. The reason we like it to be not equal to 1 is because then if b is 1, then it's not a one-to-one function. So we want it to be a function that has domain negative infinity to infinity and 1 to 1. Right, just to explain the domain thing, the reason why the base can't be negative. So let's not worry about a and k, let's just say b is negative 1. And then I want to raise it to an exponent. Let's say the exponent I want to raise to is 1/2. If it has domain negative infinity to infinity, this should come out as a real number, but negative 1 to the 1/2 is not a real number. That's because the 1/2 power is the same as the square root, and the square root of negative 1 is what we call I. But if the numbers in here is positive, then it's fine. So like 19 raised to the 1/2. Well, the square root of 19, I guess, as a decimal is around 4.36, but we get out a real number. As long as this number is positive, we get a real number. All right. The added thing, really remembering that we don't want b to be 1. You won't even see 1 because 1 raised to any power is 1, and we're not going to see that over and over again. All right, so e is a special number often used in exponential functions. Like mentioned above, it's called the exponential number. And just so you can see what it is, it's really just a number like pi. There's a button for it on every calculator. So if you want to evaluate e, the first one says approximate it to 4 decimal places. You can find e in 2 spots on this calculator. One is on the division sign, and one is on the button up here. The button says ln, and then on the second part it says e to the x. So you can do this with either one. Since we want just e, if you type in e, you see what we get here. Rounded to 4 decimal spots, 2.7183. So that's what e is. Sort of like how pi is about 3.14, e is about 2.7183. Now, if you want to do it with an exponent, you can use the E button that I just used before, raise it to the negative 3.8 power. Or if you want to use this other button, the E raised to the power, hit the second button, and it'll automatically put the power spot in for you. But that's up to you. There's not really a difference between the buttons. One's just E, one automatically puts the power in. You can see that they are the same. So this one is 0.0224. Right, but there's a few questions at the beginning of the section just dealing with the calculator, just helping you realize that this is a button on the calculator. You might have never used it before. Right, so properties of basic exponential graphs. Right, so what we're going to do is look at the graph of y equals b to the x. And we're going to look at two situations because the graphs are very, very similar, but one big difference. Remember how we said that we want b to be positive but not equal to 1? When it's between 0 and 1, we will have one picture, and when it's bigger than 1, we will have another picture. So I'm going to do the one between 0 and 1 on the left first. If you think back to when we did the parabolas, we had two pictures as well, and there was a very subtle difference. This is the same way. Almost everything is going to be the same. Let me rewrite y equals b to the x just to really emphasize that's the graphs we're looking at. All right, so there's one point that's very special, and that is the y-intercept, because when we plug in x equals 0, you might think, well, we don't know b, but it doesn't matter when we plug in x equals 0 because we get b to the 0, and anything to the 0 power is 1. So the y-intercept here is 1. I'll go ahead and plot that point here. But there's one thing that's even more important about exponential graphs. I might scroll down too far. And that is they have what is called a horizontal asymptote of y equals 0. So you have a horizontal asymptote of y equals 0. Just to rewind very, very quickly, if you have a k here, the k value is the horizontal asymptote value. Since the example we're working with, k is not written there, it's actually 0, that's why it's y equals 0. Right, and then the last thing, when b is between 0 and 1, it's actually a decreasing graph, and it follows this shape. So decreasing means as we move to the right, it moves down. It's going to stay above the horizontal asymptote. Which I'll in the future abbreviate as HA. And it has a curved pattern like this. So even though it's getting very close to the horizontal asymptote over here, it's going to stay above, and it's going to move right forever. And on the left side, it's going to go up to infinity. And it's going to go back to negative infinity. Now, the reason I want to mention that it goes back to negative infinity is it gets so steep that if you actually graph one, which we'll see in a second, it gets so steep so quickly that you might think it becomes vertical, but it does not. All right, so just so you can see the graph here, what I'm going to do is graph y equals b to the x. I'll pick b as 1/2. Actually, I'm zoomed really far out, but you can still see the shape there. I'm going to zoom back into the normal one. So what is happening here? It looks exactly like this shape. It gets really steep over here, but it's going to keep going back. And to the right, it's going to just be so close to the x-axis that it almost looks like it's on top of it, but it's actually a little above it. And if you zoom out, you can see that it's going to stay. If I zoom out again, just hit 3. It almost looks below because the pixels are off, but if you type in, let's say if I want to plug in x equals 100, you see the y value, we have 7.889 e to negative 31. That means there's actually 30 zeros over here in front of the 7. It's pretty close to 0, but it's still positive. All right. So this is the shape of an exponential graph. We will see with the one I'm about to draw, and when I graph an example, that it has the same basic properties except one. Right, so everything else is going to be the same. If I plug in 0, it doesn't matter what b is, the y-intercept is going to be 1. It's still going to have the same horizontal asymptote. It's still going to stay above the horizontal asymptote. I'm just going to draw an arrow to not rewrite that. The main difference here is when b is bigger than 1 is an increasing graph, which means as we move right, it's going to go up. It pretty much looks like this graph over here flipped over the y-axis. So as we move to the left, it's still going to stay above the x-axis, but as we go to the right, it's going to go up to infinity and right to infinity as well. But as I did with the other one, I can just draw or do an example here. For b bigger than 1, I can use 2, so 2 raised to the x. The parentheses isn't actually necessary, but it's a good idea when you have exponents with x in the exponent to write the base in parentheses. And then if you graph it, you see that it is exactly the opposite way. If I zoom back to my normal, it looks exactly like, well, as close as I can draw by my hand, like this. All right, so the key things to remember here are the increasing and decreasing thing. And honestly, you don't need to memorize the y-intercept because if we have an a value here, if we have a k value here, it's going to move. But remember that we have a horizontal asymptote. Now there are some graph transformations that can make us flip over the x-axis. So our graph can move down here, it can move left and right, up and down. You just want to have this basic curved shape down and that there's a horizontal asymptote. I guess the one thing that we really didn't touch on, we already mentioned the domain already, the infinity to infinity, the range. You'll notice here that the 0 has a parentheses on it because it stays above the horizontal asymptote. It never touches the horizontal asymptote. Right? If it actually touched the horizontal asymptote, then we put a bracket, but it doesn't. So we use a parentheses. All right, so what we'll do, I got a couple examples here to graph. Graphing these, when you use the graphing tool, one thing that is really easy to want to do, but you don't actually want to do it, is using the graph transformation rules. The reason is because you can easily get fractions when you plug them in, and you can't graph fractions on the homework, unfortunately. So here are the general rules of thumb. If you're doing it by hand, you have to do this part. The computer is going to do this part for you. All right, so the computer is going to fill in the horizontal asymptote after you graph it. But in general, it's a good idea to graph. If you do it by hand, you need to graph the horizontal asymptote because it will tell you where to stop. Right. Then what we want to do to make sure that what comes out is a nice whole number that we can easily graph, identify two x values that make the exponent 0, 1, and negative 1. Now, if you're reading that, you're going to say, well, clearly that's three x values. What you're going to do in the two problems, one is going to be an example of each. You're going to always find the exponent, that number that makes the exponent 0, but you're also going to pick either 1 or negative 1 depending on what the base is. Right, but when you do that, this will give you 2 points on the graph, which is what you'll graph on the homework. Make sure to use the curved exponential graph tool. It looks like this. And then plot those 2 points. And by hand, you'd have to make it look like the one above. The calculator, the computer will fill it in for you. Okay. All right, so first one, g of x equals 1/3 to the x minus 2 power. What x value makes the exponent 0? Well, you can probably just look at it and say, well, if the x is 2, then 2 minus 2 is 0. Well, that's what we want to start. So what we're going to do is plug in x equals 2. And we get g of 2. The y value is 1/3 to the 0 power. And anything to the 0 power is 1. All right, so what this is telling you is there 2, 1 is a point to plot. We plugged in x equals 2, we got out y equals 1. Now the question is, what other x value do we want to plug in? When you have a fraction, you can do both and then try both. So what x value will make the exponent 1, what x value will make the exponent negative 1. But I'm going to give you a little shortcut here. What x value for this one makes the exponent negative 1, exponent negative 1. Now the reason I'm picking negative 1 here and not 1, we do negative 1 for a fraction, and we do 1 for a whole number base. Okay, so the way you pick the second one, you always want to pick the x value that makes the exponent 0, no matter what. For the second point, you want the x value that makes the exponent negative 1 if you have a fraction inside, and 1 if you have a whole number inside. Right. And for us here, we want negative 1 because we got a fraction. If x equals 1, then 1 minus 2 is negative 1. and we get g of 1 equals 1/3. 1 minus 2 is -1. And to remember what a negative exponent does for us is it tells us to flip the fraction inside to make it positive. All right, so we flip the 1 over 3 to 3 over 1. Then it makes the exponent positive. And anything raised to the 1 power is just itself, so this is just 3. So the other point we're going to plot is x is 1 and y is 3 is the other point. If you plot these 2 points with the exponential graph tool, you will get the correct graph. I'm going to just show you what's going to happen. So x is 1 and y is 3. That's one of our points. Then x is 2 and y is 1 is another one of our points. And it's going to make the graph for you. It's going to make that curve shape as long as you pick the correct graphing tool. And it's also automatically going to fill in the horizontal asymptote. It's not going to draw the dashed line, but it knows it's there. All right, so ultimately, your goal for these problems is to find 2 points on the graph and use the correct graphing tool. All right, so the next one's going to be pretty similar, but also a little different. I wanted to make sure we hit on one like this. All right, so this one we want to graph f of x equals -5 to the x plus 3 power. All right, start off. What x value makes the exponent 0? Well, that would be -3. So we plug in x equals -3, we get f of -3 equals -5 to the 0 power. Now anything raised to the 0 power is 1, but only 5 is being raised to the 0 power. The negative is out front. All right, so if you want to simplify this, which you really need to because you got to plot it eventually, 5 to the 0 is 1, and we got the negative out front. All right, so our first point we're going to plot is -3, -1. All right, now for the second point, what do we want to make the exponent? Since we have a whole number base, we want to make the exponent 1. Well, if we want to get 1 here, -2 would work. If we plug in -2 for the exponent, -2 plus 3 equals 1. Now, if you get messed up here, it's going to be either -2 or -4 because it's going to be right around -3. So you can try both. And we get f of -2 equals -5 to the 1 power. Anything to the 1 power is just itself, so 5 to the 1 power is 1, and we got the negative out front. So we got -5. So the other point we're going to plot is -2, -5. Right, now we're going to plot the 2 points. Using the correct tool. Once again, it's going to fill out everything, but you have to use the correct tool and plot the correct points. So we got -3, comma, -1 is a point, and then -2, comma, -5 is our other point. Now you'll notice this one is below the x-axis. That's okay because this negative out front flips us over the x-axis. Right, it's going to fill in that horizontal asymptote automatically, and it's going to make the shape for you. Right, since this one is closer to the asymptote than this one, it's going to go back and get close over here, and then it's going to fly away, but this time it's going down because it's going to stay away from the x-axis. It's going to stay away from the horizontal asymptote. Since this one's below it, it stays below the whole time. But that is exponential graphs. Now, the last little bit in this section is word problems involving exponential functions. What I find is that these are not nearly as involved as other word problems, but you do have to make sure you know how to come up with the equation. So one thing, how do you tell when you should use a word exponential function for a word problem? So the most important thing to identify a word problem involving an exponential function is the usage of something increasing or decreasing by a percentage. Sometimes it says in proportion, but usually you're given some type of percentage, or it'll just say use an exponential function. All the word problems use the equation f of x equals a times b to the x. And like with word problems we've seen before, x and f of x don't need to be that. They can be represented by different letters in the problem. Right. But once again, if you're on the final, if you're dealing with a word problem and you're reading it and you have to come up with the equation, you know to use this if you see increasing or decreasing by a percentage. Okay. So we got to read this word problem here. A population numbers 15,000 organisms initially and decreases by 8.9% each year. Well, even though this will mean something more in our problem, this decreasing by a percentage means we want to use f of x equals a times b to the x, since it's a percentage. It says, so suppose p represents population and t the number of years of growth. An exponential model for the population can be written in the form p equals a times b to the t. So they're actually giving you the equation. The question is, what is a and b? Well, there's a really nice property of exponential functions in that a is the initial amount. And that's always the case. A is the initial amount for something of this model. And here we have 15,000 organisms initially, so it's 15,000. Now, what is b? B is the thing being raised to the t power, so that's really the base of the exponent. It's related to the percentage change. What you do, this is going to sound kind of weird at first. You start with 100%. And then we read the question. It's decreasing. Since it's decreasing, we subtract. If it was increasing, then we would add. And then what we do is since it's decreasing, we subtract the 8.9%. Okay. All right, so 100, if you want to subtract percentages, they're both percentages, so just subtract the numbers. 100 minus 8.9 is 91.1%. Now, one thing in math is that we don't use percentages unless if the answer wants a percentage. You must change to a decimal. And remember, to switch from a percentage to a decimal, we divide by 100. If you want to go from decimal to percentage, you multiply by 100. Right, so we take our 91.1, divide by 100. It's going to have the same effect as moving the decimal place to the left twice, and we get 0.911. And that is B. All right, so B is 0.911 and A is 15,000. We're not asked to do anything with this equation, so that's it. We just wanted A and B. All right, the next one is going to be very similar to this, but then we'll do something with the equation we get. So this one says the fox population in a certain region has an annual growth rate of 7% per year. Once again, percentage means we have the function p equals a times b to the t. The reason I'm using p and t instead of y and x, I'm just using p for population and t for time. But this is telling us it's exponential. All right, so just like the last problem, we want to start by figuring out what is a and b. T is our variable, p is our other variable. We want a and b. Right. It is estimated that the population in the year 2000 was 17,700. And we want to find a function that models the population t years after 2000. So the initial time, t equals 0, is the year 2000. And what is the initial population? It's 17,700. So that is what A is. All right, remember with this exponential model, the initial amount is A. All right, now for B, we know we have to adjust based on the percentage of change. We start with 100%. This is growth, so it's plus. All right, last problem, it was going down. This one's going up, so it's plus 7%. 100 plus 7 is 107%. And remember, this is not actually B. We have to change it to a decimal. So you divide by 100 or move the decimal place that's right after the 7 over twice. Either way, you should get 1.07. But this time it actually wants the function. It wants the equation, so you cannot just write down what A and B are. You need to plug them in. So P of t equals A, 17,700, times B, 1.07 to the t power. Right, now you cannot combine the 17,700 and the 1.07 because one is being raised to the exponent and one is not. So the way you can think about it is they have different exponents. One's the exponent is 1, the other, the exponent is t. Okay, so if you multiply those two numbers together, you will get it wrong. It has to be this. Part B says, estimate the fox population in the year 2008. Well, since our starting time was in the year 2000, this is saying plug in t equals 8 and solve for the population p. We made our equation here. Now this part's super straightforward. We just plug in 8 for t, we got p of 8 equals 17,700 times 1.07 to the 8 power. Now, if you have a different kind of calculator, you might not be able to do all this at once. You need to do the 1.70 to the 8 first. And then multiply it by 17,700. With this calculator, we could have just done it all at once, but with an older one, you want to do it like that. And since we're talking about a population of foxes, you want to go ahead and make sure, excuse me, you want to go ahead and make sure that you round to the nearest whole number. We get 30,412. All right, so we got a couple more just to really practice it. This one is kind of taking the last problem, but doing part B all at once. This one says a vehicle purchased for $27,500 depreciates at a constant rate of 9%. Determine the approximate value of the vehicle 12 years after purchase, round to the nearest whole number. So you can use your y and x as whatever you like. Let's say we have the vehicle v, its price. Since we're talking about a percentage, here we got equals a times b to the t power. And really the question is, what is b after 12 years? All right, so we'll do exactly what we did last time. We'll figure out a and b, and then plug in the appropriate t. A is the initial amount. It's the amount you bought it for, which is the 27,500. Now depreciate means it's going down in value. So this is how it's related in B. It's decreasing, it's going down. So we start with our 100%, subtract off the constant rate of 9%. 100 minus 9 is 91%. And switching that to a decimal is 0.91. All right, so when we plug in A and B, we get its price, V equals 27,500 times 0.91 to the t power. Right. And now to finish this problem up, we want to determine the approximate value of the vehicle 12 years after purchase, round to the nearest whole dollar. Well, this is telling us to plug in t equals 12. So we get v equals 27,500 times 0.91 to the 12 power. And when we do that, round to the nearest whole number, we get $8,868. Right? And if you've ever owned a car for 12 years, you know that it's not going to be worth that much after 12 years. This problem is a little ambitious as to how much a car is worth. Right, so the last pair of problems here deal with financial stuff, interest rates, and the formula for each one is given. And I'll go ahead and say that the formulas for these will be given, at least for this one, will be given on the test. You won't have to memorize this, but you will have to memorize this, but we'll get to this afterwards. All right, so a bank features a saving account that has an annual percentage rate of 2.5% with interest compounded quarterly. Santos deposits $4,500 into the account. All right, so I'm just going to underline the numbers here because they're probably going to be important. The account balance can be modeled by the exponential function s of t equals p times 1 plus r over n to the nt power, the messy formula, but it's given to us, where s is the future value, p is the present value, r is the annual percentage rate as a decimal, n is the number of times each year that the interest is compounded, and t is the time in years. Now, if you go back up to the above, the n is kind of the weird one. That says this is compounded quarterly. If it's compounded quarterly, the number of times that it's compounded each year is 4. Quarterly, 4. So it's actually telling you right here n equals 4. It says p is the present value. That's the amount that's deposited. So p equals this 4,500. And then r is the annual percentage rate as a decimal. So we want to make 2.5% a decimal. That's 0.025. You move the decimal over twice, would add a 0 in there. Or if you divide by 100. So 2.5 divided by 100, 0.025. And oddly enough, I didn't even realize that, but that was part A. We've actually done part A already. What values should be used for P, R, and N? So P is 4,500, R is 0.025, and N is 4. Right, so it can be compounded a lot of different ways. Annually is just 1. Monthly would be 12. Daily would be 365. Weekly would be 52. And quarterly is kind of the weirdest one, but it would be 4. All right, so now to use this formula, how much money will Santos have in 7 years? So it's telling us, along with this stuff, plug in t equals 7. So we get s of 7. This will be the amount of money in 7 years. P is 4,500. We got 1 plus r is 0.025 divided by n, which is 4, to the n times t power, 4 times 7. Now, you might want to simplify it a little bit before you type it all in the calculator. So I'm going to simplify the inside here. 1 plus 0.025 divided by 4. So the way this is written is exactly what I want because I didn't put parentheses around it. We get 1.00625. And then 4 times 7 to the power is 28. And now this looks a lot like what we were typing in before. So let's do that. 4,500 times 1.00625 raised to the 28th power. And we got $5,357.69. All right, so in 7 years, if you deposited $4,500 into a bank account that gets you 2.5% interest and don't do anything else, it'll be up to this amount. You can see that you made around $800 for doing absolutely nothing. But anyone that's ever had a bank account knows that this is a very high percentage. It's highly more likely to be around a 0.5% if you're lucky. All right, so the next one is the same kind of theory, but compounded continuously. So when interest is compounded continuously, the formula becomes a lot shorter. Notice I underline continuously because it's very different. And we see that number E pop up. So S of t equals PE to the RT, often known as the PERT formula. So E is that 2.71 from before. When it's compounded continuously, it means it's just constantly going. Every time you take a breath, every time you blink, it's being compounded. It's adding your interest. So it says you deposit $6,000 into an account earning 8%. And we know 6,000, the amount you deposit is P, earning 8%. Our interest rate R, we divide that by 100 and we get 0.08. And compounded continuously means there's no N. It just means use this formula. And we are asked, how much will you have in the account in 10 years? So it's asking us, when we plug in t equals 10 along with our p and r, what is the amount? All right, so we get S of 10 equals P is 6,000. I don't need that, parentheses, times E to the R is 0.08 times T, which is 10 power. Now the one thing I would do here before you type it into the calculator is simplify the exponent. 0.08 times 10 is 0.8. All right, so we saw to do that, do this at the beginning of the section. We just have a 6,000 in front now. E raised to the 0.8. And you get $13,353.25. Which is round where it tells you to round. Right. When it's compounded continuously, that means every single second it's adding in your interest. And if you ever want to compare saving accounts, how much interest you're going to get, compounded continuously is always the best if you get the same percentage. And so if we went through and did this problem, part B, but we did it continuously, meaning we did use our P equals 4,500, our R is 0.025, and then our T is the 10 again, or sorry, the 7, you would get a bigger number than this. It's not a part of the lecture I have, but I'm going to go ahead and just do it anyway. So imagine our P was 4,500, E raised to the, oops, and then R in the previous problem was 0.025 times T, which was 7. And if you compare that here, you actually get $3 more. Doesn't seem like a lot over the span of 7 years, but it's still free. And over time, it can get a lot bigger. But that is what we need to know for exponential functions for now.